Good morning, everyone. Today we are going to perform the practical on Rayleigh scattering calculations. Rayleigh scattering is a dominant intrinsic loss mechanism in low absorption window between ultraviolet and infrared absorption tails. So if we look at an expression that we have to calculate is, first we will be calculating the Rayleigh scattering coefficient. So Rayleigh scattering coefficient is given by gamma R is equivalent to 8 pi q by 3 lambda to power of 4 into n to power of 8, where n is the refractive index of the cone, into p, that is the photoelastic coefficient, p square, into compressibility constant beta c, K Boltzmann's constant, into fictive temperature. Now after we have our Rayleigh scattering coefficient, the next we have to calculate is the loss factor, which is given by L is equivalent to exponential minus gamma R into L. The unit of gamma R is per meter, and while calculating the loss factor we will take because we need the loss per kilometer, so we will be so while calculating this L has to be L will be 1 kilometer and has to be converted into meters, that is it will be 1000 meter. Then we will be able to get our loss factor per kilometer. Now once we have the loss factor, the attenuation, that is alpha in dB per kilometer, because for loss factor we have taken L to be 1 kilometer, it is equivalent to 10 log of 1 by loss factor. Once we have our alpha, we can calculate the output power as PO is equal to PI into 10 to power of minus alpha L by 10. And we can also calculate or we can convert this output power into pulse by multiplying by the Gaussian factor, as we have done in our experiment number 2, as e to power of minus x square, multiplying it by e to power of minus x square by 2 sigma square, where x is our counter and sigma is the pulse width. Aim of doing this experiment is first calculating the Rayleigh coefficient, then calculating the loss factor, then calculating the attenuation, and repeating what we have done in experiment number 2 using these relations. So first we'll start by selecting our input parameters. Since these are the constant, what will be, so first we will select our numeric nanometers. After wavelength, the next parameter that we want to input is our relative refractive index. Sorry, the next parameter that we have to input is our refractive index of the core. The other parameters that we require as an input is the length in kilometer. Then we need the spectral sigma value, the spectral width in nanometers. Now we have all our input parameters. Now what all we want to see at an output is an input pulse. Then we need to see the output for this both. Like last time, we will be using extended XY graph. As you know, it gives a better control. It gives us a control over the time axis. Okay, in addition to this, we would like to see our Rayleigh scattering coefficient and the alpha. So for that, we will be using the gauge. And the attenuation. Okay, now we will go to our block diagram window by pressing Ctrl E. Now we know that for this performing or getting the Gaussian pulse, we need to have everything in our structure of for loop. So I'll just select the for loop and set the counter at 50 by create constant, sorry, counter at 100. There's a spelling mistake in wavelength. Okay, so first calculating the Rayleigh coefficient. As you see, there are a lot of parameters in it. So for doing this calculation, instead of using multiple multipliers, what we can do is we can use a formula book. For that, just click on this mathematics, go to script and formula, and then select this formula. Okay, now here we can give the parameters. So first I will name the, so in the formula book, first we will be naming our variables that we will be using. So x1 I name it as wavelength, x2 as refractive index of core, or I can just give them the variable name in lambda. So once we have this, now for Rayleigh coefficient, what we will do is, it is 8. We'll simply write our formula 8 into pi cube. So for the power, we will just use this double square. 8 pi cube, it's divided by lambda, that's the wavelength, lambda to power of 4. So first we will just use proper brackets into, we have core refractive index to the power of 8 into, there will be, we need to define one parameter p, then we need to define beta c, and we need to define Boltzmann's constant. We can directly write Boltzmann's constant here, and the effective temperature. So it is the power of 8 into, we have p square into p square into beta c. You can directly write beta c here. It is, for the given problem, it is 7 into 10 to power of minus 11 into k, Boltzmann's constant, which is 1.38 into 10 to power of minus 23 into fictive temperature. You can see here it's an invalid formula because it's incomplete. We need to check whatever anywhere we missed any brackets. And now we can clearly see we have written the Rayleigh scattering coefficient formula 8 pi q by lambda wavelength to power of 4 into n to power of 8 into p square. Here P also we can directly write the constant value for the fiber. It's 0.286 into isothermal compressibility into Boltzmann's constant into fictive temperature. The fictive temperature is 1400. So either we can write it here only. So as you can see, we have wavelength and n. We can just rearrange them. And now we can see the input wavelength can be given to our input parameter. The core refractive index can be given to this. And what we are calculating is the Rayleigh scattering coefficient, which can be given to this. So this is how we have calculated our Rayleigh scattering coefficient. The next task is calculating our loss factor, which is exponent. We know that our loss factor is equivalent to, as I have already written, is exponential minus gamma r into L, where L is 1 kilometer, and since the unit of gamma r is per meter, this L has to be replaced by 1,000. Okay, so what I'll do is simply I'll use multiplication, and here instead of taking link length, I'll just directly take, because the link length is fixed, I'll take it to be constant 1 kilometer. We have now gamma r L, we need to negate it. So it's minus gamma r L into, it has to be exponential. So what are we supposed to calculate? Our attenuation alpha L, it is equal to 10 log of 1 by loss factor. So our loss factor is calculated. What we will do is we will invert it by going to the mathematics, numeric, and we need to go to mathematics, exponential. Now we need to have log 10. Now multiply it with 10, again numeric, multiply, and here you can add the constant 10. Output power pulse, PO, which is equivalent to, PO is equivalent to PI 10 to power of minus alpha L by 10. Okay, so what we will do is we will again start calculating this parameter. For that we need a multiplier, numeric, multiply, we have alpha, we need to multiply it with L, this alpha, multiply it with L, we need to negate it and divide it by 10. For 10 we'll create a constant, right click, create a constant. Then we go to mathematics elementary, exponential power of 10. So now we have our PO calculated, but we know that it's not in the form of a pulse. To make our output and input pulse, we need to um, mathematics, numeric, square, sigma square. Now we need to multiply it with 2, elementary, multiply. Here we'll create a constant 2. We need to square it and then negate it. Now we need to divide this term by this term. So for that we need to be very careful. In case you inverse it, the output plot will be also inverse. So now we have minus x square by 2 sigma square. We need to multiply by pi as well as PO to get our pulses. So to get our output pulse and input pulse, we have to have multipliers. So this is my output pulse. It needs to be multiplied by this Gaussian parameter. This will give me my output. Similarly, for my input, again I need to select one multiplier. Input multiplied by the Gaussian pulse. This is my connected to y. Now x, as we know, is a counter which needs to be connected by x minus 50, the counter. And here also the x is to be multiplied by the. Okay, now we have to reach at the reset button. We need to create a constant and make it false so that it does not continuously resets again for both the devices. Now our whole setup is ready. We can now test it whether we are getting an output or not. You can see our plot is inverted. We need to check what is wrong with our plot. Now to rectify it, what we see is we calculated minus x square by 2 sigma square, but we did not calculate e to power. So we just need to correct this. I'll just delete this portion and add mathematics, elementary, exponential. So now we get e to power of and run and see. Yes, you can clearly see your input and the output one. So control E. Now we can see that we are getting the pulses. We can see the impact of the wavelength. As you can see, the wavelength is increasing, the output is increasing. So this is what you have to do in your experiment number 3 of identifying the output power at various wavelengths. Thank you.